Okay, so we have been leading up to the residue theorem, right, in the form of our discussions relating to Taylor series, uh, Laurent series, expansions of functions which are analytic and which have some analyticity, non-analyticity in some region, but where analyticity is available in an annular region. And we have seen how a Laurent expansion becomes possible. So in this lecture, we will see how when we have functions which have isolated singularities, right? So it becomes possible to work out certain contour integrals, uh, using just the residues, right? So we have looked at the idea of a residue, but we will see how it plays out. Why it's so important is something we discuss in this lecture. Okay, so if we have a function f of z that's analytic in an entire region except for an isolated singularity at some point z0, then we know that there is a valid Laurent expansion which we can write down where all these positive powers in z minus z0, they form the regular part, and then you also have these coefficients b, b1, b2, b3, so on, and they together form the irregular part, right? So that's where the singularity is. So b1 over z minus z0, b2 over z minus z0 square, so the whole square plus, and so on, right? And this expansion is valid in some region 0 less than mod of z minus z0 less than epsilon, because you have an isolated singularity at z0. So now we will see how among all these coefficients b1 has a special name associated with it, because uh, it has some special importance, as we will see. And so the way to see that is to actually just perform a contour integral, over a circle, let's say, right? So over a circle whose radius is r, and which is centered about this point z0, and where this radius r is less than epsilon, right? So that you're in this region where this expansion is valid. And now we have seen that you can go ahead and exchange the integral and summation because of these uniform convergence properties. And so we are performing this contour integral in the anti-clockwise direction, right? So therefore we can go ahead and write this contour integral of f of z dz over c to be just summation over n goes from 0 to infinity, an contour integral z minus z0 the whole power n dz plus summation over n, again n goes from 0 to infinity, bn contour integral of z minus z0 the whole power minus n minus 1 dz. Okay, so now we invoke a result we have used many times. So we have seen that whenever you have a function like z to the n dz, and if you take a contour integral around the origin, which in a closed contour which encloses the origin, we have seen that for all integer values or n, this contour integral will vanish except when n is equal to minus 1. 1 over z is special, and that gives you 2 pi I. And so this result generalized to some other point z0 is the result here, which is that contour integral over c z minus z0 the whole power minus n minus 1 dz is equal to delta n comma 0 2 pi I, right? So here I am not even specifically stating that all these positive powers go to 0, right? So that's self-evident, because after all these functions z minus z0 to the n, they have this analyticity properties, right? So in any case, so this result holds, and therefore we have this contour integral f of z dz is just given by 2 pi I times b1, right? So so in this case, I mean, we have a singularity sitting at z0. So it's I mean, even with the singularity present, it's still true that even when you take a contour integral of c over c z minus z0 the whole power n dz is going to be 0 for all these powers except for 1 over z minus z0, right? So that's why this coefficient b1 is of such great importance. right? So I mean, this result is something that we have worked out explicitly by writing down the contour integral as just an integral over theta. So in other words, write down z as z naught plus r times e to the I theta, and then perform the integral, and then explicitly verify that indeed all of these integrals will just vanish except 1 over z minus z naught, when you get 2 pi I. Right, so we have this result that integral of over c f of z dz is 2 pi I b1, but b1 has a special name, and it's called the residue of this function f of z at the isolated singularity z equal to z naught. So this is the reason why this coefficient has a special name. So in fact, this contour does not have to be a circle. It can be an arbitrary shaped object, as long as it's a closed, simple closed contour which encloses this singularity, and it encloses no other singularity, right? It should enclose only one singularity, and it should also not not pass over a singularity. It must lie entirely within the region of analyticity, right, and enclose this singularity inside it. So in fact, this result can be generalized to include many singularities, and so that's the theorem which we state. It's the residue theorem. So if f of z is analytic on and within a closed contour C taken anti-clockwise, except for a finite number of isolated singularities. So basically, it's a nice function. It's an analytic function except at these points, right? So what the residue theorem tells us is, if you're taking a contour integral of such a function over which encloses a finite number of these isolated singularities, you just simply take so it's actually summation over this. So the result is equal to, I should have said, summation over all the bi's, so which adds up to, which is going to give you 2 pi I times summation over k residue at each of these singularities z equal to zk fz. Right, so basically what we are saying is, so you have a function, and which is analytic in this entire region, except at let's say there is a singularity here, there is a singularity here, maybe there is a singularity here, right? So yeah, you can come up with there is this theorem which we discussed, which allows us to deform these contours. So whatever the value of the integral is around this contour is basically the same as the value of let me try to redraw this. Let me actually erase this entire thing, and then I will argue that the value of this contour integral is the same as if I were to do something like this, go around here, and then come back down this path, and then go around here, and come back around here, and then go like this, and then maybe come up with a contour like this, and then basically you can make each of these small circles, you can make it exactly like a circle, and very tiny ones which pertain only to those isolated singularities to take care of the direction. But basically you can argue that the value of the contour integral along paths like these will cancel each other out, right? Along this direction and along this direction, opposite direction. So here it's coming in this direction, so here it's going to be coming in this direction. So they cancel each other out. So in the end, you're left with just the contour integral around this point, and around this point. All of them have to be added, and then each of these separately by the residue theorem is just going to be this residue 2 pi I times the residue at that point. So therefore it's clear that the overall result is going to be 2 pi I times the sum of the residues, because they are finite in number. Let's look at a few examples where this theorem holds out. So suppose we consider a function like f of z is equal to z plus 1 divided by z squared plus 9. So we have already evaluated the residues. There are two singularities, there are two isolated singularities for this function. One of them is located at plus 3i and the other one is at minus 3i. Both of them are simple poles. So the way to evaluate the residue at these 2 points is to simply multiply by, in the first case by z minus 3i, and take the value of this new function at the point z equal to 3i. So that gave us, we have already done this exercise, and the residue is, we found it was equal to half minus 1 by 6i. Again, to find the residue at the other point, z equal to minus 3i, it's going to be z plus 3i times f of z, and then we have to put the value z equal to minus 3i. So which we evaluate to be half plus 1 by 6i. So considering the contour C in the anti-clockwise direction, and it has to be a contour which encloses both of these singularities. So let's take, for simplicity, a circle of radius phi which is centered above the origin. So clearly both of these singularities which are at plus 3i and minus 3i are also included, and so we can evaluate this contour integral to be just 2 pi I times half minus 1 by 6i plus half plus 1 by 6i. Both have minus 1 by 6 and plus 1 by 6i is cancelled, so we're just left with 2 pi I, right? Very simple answer for what looked like an apparently quite a difficult problem. If you had to work it out the hard way, writing down, for z, putting down r times e to the I theta and so on, it would be quite a messy task. But so we have already reduced this sort of difficult problem to just calculating residues. So that's where the power of this approach comes from. And also we know from this principle of deformability, right? I mean, it did not have to be a circle. It could have been some other more complicated object. If you have to evaluate that, then it's a nightmare if you have to do that directly from first principles. But residue theorem allows us to compute it with ease. So let's look at one more example. Again, so this function has it has a pole of order 2 at z equal to 0, right? We've seen this 1 over z times e to the z minus 1. So we can write this as phi over z divided by z squared. Phi of z has this expansion 1 over 1 plus z over 2 factorial plus z squared over 3 factorial, so on. As we've seen, the residue can be computed by taking the derivative of this quantity at z equal to 0, and it turns out to be minus a half, right? So you can go over this calculation of the residue again if you wish. So you see that it's important to be able to calculate residues. If you can work out residues, then you can work out these contour integrals with ease because of the residue theorem. So since the residue we already have worked it out is minus half for this, so if we consider the contour C in the anti-clockwise direction, a simple closed curve, which for simplicity we can just take it to be the unit circle centered about the origin in this case, because there is only one isolated singularity, and that is at z equal to 0. It's a pole of order 2. We have already worked this out, and so it's simply a matter of writing down the answer now. If you were to take this contour integral, it's going to be 2 pi I times minus a half, so it's just minus pi I. Very straightforward. Okay, so there are more examples which we can consider. Perhaps that's going to be part of the homework, but the key idea already comes out with these few examples. Right? So the residue theorem can be used to compute contour integrals of this kind, which in turn, used cleverly, can be used to evaluate many interesting integrals of definite integrals of a real variable. Right? So some of those examples also we will look at. But as far as this lecture is concerned, it's primarily about seeing how the residue theorem plays out. Right? We've stated the residue theorem. We also argued for how it comes about and shown a few examples of how to make use of the residue theorem. Thank you.